I think we are ready to start. I waited the 2 to 3 minutes after the official time. Great. So hi, I'm Alex. I'm here today to talk about SuperRecord, or stepping back a little bit more. Basically, I want to talk about what anonymous records or what structural types might look like implemented as a library in Haskell. So the talk is very Haskell heavy, because I'm implementing the system for Haskell. But I assume that some ideas, at least of it, can be applied to other similar or related languages. So to kick this things off, let's talk about a small motivation, why do you want structural types or records anyways, right? Because in Haskell you already have records or nominal types. So what would be a use case for this kind of thing? So one thing I wanted to mention that has been going around the internet a lot too is this reader T env pattern. So basically, anytime you're writing an application in Haskell, there's this pattern or this guide that a lot of people use saying, well, your application or your main application is not going to run in the I/O monad. It's going to run in a reader T monad on top of I/O. And in that environment, you're going to carry things like, for example, your configuration, right? Like if you're doing a web server, what port are you going to run on? Or if you're doing logging, where does your logger live, right? You want to do HTTP requests. You want to have an HTTP client maybe in your environment that you can reuse, right? That keeps connections open that you use frequently. And very important, a database connection, right? That's something that your application will probably need throughout the whole stack. So what you end up doing is, well, you define a type like this, and then you define a type synonym here saying application M is a reader T of my environment and then M, and then that's what you're going to write all your logic against. So if you think about this reader T env pattern, well, what would a function in that world look like, right? So here I wrote a example function. It's obviously a very example I just put together here, not very realistic, but let's consider this function, and this runs in our app M we just defined, and well, it needs the client, HTTP client, it needs the logger. Then we do some downloading using this HTTP client which we just acquired, and then we log the results somewhere. We don't care about this. So what is a problem about this function when you look at it? Well, it takes the whole app M here. So that means this function, in the type, says I have a dependency on the whole environment, right? So even though this function, if you go back one slide, even though this function here doesn't use a database, for example, in my type, I'm claiming that it needs the database, right? So if I were to write a unit test for this, for example, I'd have to set up a dummy database, right? And that's a little bit annoying and also makes it kind of hard if your application grows larger and larger to refactor things because dependencies become blurry again, right? So basically one idea here is what if I could more explicitly state what this function actually needs without needing to define a new environment that doesn't contain a database connection, right? So naively you could say, okay, well I'll just define env prime, and env prime doesn't have a database connection inside. So we'll look into how we can solve this a little bit later. Wrong direction. Cool. Another thing that you can think about is, let's say you're writing a compiler and you have a compiler pipeline, and throughout your compiler pipeline, what you'll do is you'll work with an expression, right? So the expression can be an integer, or you add 2 expressions, or you negate an expression. And basically, all your expressions are annotated with some generic annotation, right? For example, when you parse your expression, right, you will parse an expression, and all your expressions will be annotated with the position where you parsed it from, right? Because later on you want to do nice error messages. In your type inference function, well, you take this thing with the position. You need the position here because you want to report error messages when there's a type error. And you give back a new expression that keeps this position around because maybe the next step in the pipeline will still need it. And you add in the type you inferred for all your expressions, right? And you can do imagine other steps. Well, now you have a flow analysis maybe that takes the position of the type and adds something to it. Or you have like an optimizer that, well, it doesn't really care about the position anymore because it doesn't need to like report anything on that, but it needs the type and like the flow information, and then just gives you back an expression of type. So here again, you see this problem that you always need like a set of, like here you need the position, here you need type and flow info, here you output more, and you can't just simply compose these, although theoretically it should be possible. So basically, if you had a way of like formulating this more open, saying that, well, here we don't need a type and exactly a type and a flow info, but more we need something that has a type and a flow info, right? So something more open here. And the same goes for JSON APIs, for example. So let's take this example from Servant. So basically, the idea in Servant is that you formulate your whole API as a type, right? So this thing says, well, you have an endpoint that is users / and then like some query param you pass in, and it returns here a JSON formatted user, right? And your user is this Haskell-Type. Well, this is really great. Now you have like basically almost the whole structure of your API on type level, right? So you can generate a client for it, and you can generate docs for it, but what if you want to know what this user actually looks like on type level, right? You don't really know that. So what if instead of like using vanilla Haskell types here, what if, oops, well, we'll see later, but what if the structure of this was actually also on the type level? And then you could generate like more rich documentation or clients from that. And there's a bunch of other use cases that I won't go into depth now, but if you consider, for example, SQL ORMs that like map SQL's SQL, a DSL for writing SQL in Haskell, and you want to do joins, well, there's no first-class operator to bring together two, Haskell records, right? So there's no, like, you can't really first-class combine two Haskell records, or you can't create a new record on the fly that just contains like a fewer fields that you need. So this might be like a use case, right? Or if you're talking about FFI and you want to quick and dirty, like write a binding to a C library that has like a struct, well, you could formulate these structs without having to define a vanilla Haskell type. And then code generation, which I already mentioned. So let's dive into anonymous records. So basically, in Haskell, we have these nominal types, right, where you give a thing a name, and then that's what you work with. And other approaches in like pure example, PureScript, TypeScript, and Flow, they have this thing where they have like first-class records. So instead of defining your data person that has a field with a name and an age, and then you build it up here, basically you write something that looks similar, but you're not talking about a person thing, but more about the structure, right? So this is a thing that has a name and an age, and then this is just the technical thing that we need for the implementation here. And we can make this quite ergonomic, actually, because with the new overloaded labels, which we'll see a little bit later, we can actually, instead of having to reflect things on type level, we can actually use this hash name syntax here to bring the label name onto the type level. So what's the type of person now? Well, the type of person now is record, and then we have a type level list that tells us, well, the name symbol is mapped to a string, and the age symbol is mapped to an int, right? And that's the type of this person thing. And now we can go ahead and we can write functions. So we can say, well, in this greet function, I'm looking for a record, and all I care about is that this record has the field of called name, and that has the type string. And then I can go ahead and implement this function. And now basically any of these three records I write here will work and type check with this function, right? So person 1 only has a name and an age, that will work. Person 2 has only a name and nothing else, that will work too, right? Because this constraint, name and string, is fulfilled. Person 3 has some extra thing here, favorite color, and also name, and that will work too, right? So there's no need to like do any data transformation anymore. And if you compare that to like a greet in the with the vanilla Haskell records, well, here you can only ever have a person that has exactly those two like name and age fields. You can never have something else in this place, right? So if you revisit like our pilot pipeline as I presented earlier, now you can say in your parse function, well, this is a parser that returns something that has at least a position, right? Or if you have the type inferencer, you say, okay, I require that the record has a position, and I give you back something that has everything that you gave me, plus I will insert a new thing into it, which is the type thing mapped of type, right? So you're talking more abstract. You have something there. You're talking about what the shape of it is, but not what it actually is. And this same example for the JSON thing, right? So now you say, well, the user is not a vanilla Haskell type anymore. It's just a type synonym. And here I'll just have this records thing. And now on the type level, you have the full structure of this thing. And you can do a lot richer stuff on it, right? So how do we implement this, right? So I'm going to start with the very first simple implementation here, how this might look in Haskell, and then we'll iterate from there and see how we can do better, or how can we improve this. So what do we have to do, right? So first, we just want to make a nicer syntax for tracking these like tuples at type level. So what we're going to do is we're going to define a data type that basically has two, it's like a tuple, so two fields in a infix notation here. So basically the label of kind symbol, which will be, the label, the key of the record, and then the value, which is going to be the type of our value. And then on top of that, we're going to create our record data type, which is a GADT, right? So my record will have a type level list here, that's the XS, and it'll have two constructors, right? One is the empty record, and this is trivial, which it just has a type, well, we don't have any fields, so it's an empty list. And then the second case here is, well, we're going to add something to our existing empty record. So first, we're going to have to lift the key of the record to the type level, right? So basically, the typical way to do this in Haskell is to use proxies. And with the overloaded labels function, you can actually get this nice pound syntax, saying like pound name instead of saying proxy, and then or using type applications with the @ sign to lift things up. Then you're going to pass in the value, which you want to const to the record, and then you pass in the existing record, and what you get back is, well, a new record that knows that key is of type value and everything that was already in the record, right? So you prepend it on the front. This is very similar also to how you would implement heterogeneous lists in Haskell. And then once you have that in place, basically creating something is very similar to what we saw earlier, right? Like basically I added some like nice operators to make this look more like a record, but this is like if you would just use the code that I just showed, this is how you would construct a record, right? So basically you just list your constructors, you do proxy, colon proxy here. So this is like very vanilla without any syntactic sugar or any operators to make this feel and look nicer. Right, and then the type you get obviously is you have foo and bar, and the type, this can actually all be inferred, right? So there's no need to add any type annotations here. And now, once we have this, we know how to construct things, right? But now we also want to read fields from our record, right? So we need some way of knowing how, given this structure, how can we figure out, given a key, what is actually the return value if I read from that field, right? Because if you have this list here, and you come with a key foo, you need the type system to know, well, if you come in with a key foo, then our get function will always return as a bool, right? So you basically write a short type family which says, well, given this key and this list of key value pairs, if the keys match up, then that's the value here that will be returned if I read this, right? So there's some caveat here in the sense of, well, what if a key appears multiple times, right? In this case, we will have this restriction, or we can enforce a restriction that every key can only appear once. But you could theoretically also deal with these cases. And in the other case, well, if your key doesn't match the key that's at the head of the list right now, then basically you look at the tail and continue to recurse. And so if you reach an empty list, then basically you will get a type error that's saying that there is no value type family for this key that you provided. What you can also do is use the type error or custom type error functionality in GHC, and where you can then construct your custom type error messages that would actually like yell at you and say, well, the key you provided doesn't exist, instead of having a generic type error saying, well, this type family can't be inferred or checked. Cool. And now we can go ahead and read this record, right? So reading this record is actually a little bit more tricky than in a heterogeneous list, because the problem is in a heterogeneous list, you can just like go by field until you arrive at the index, and it's natural. But here you also have to make sure that the key you're looking for actually matches up with the key at the position you're currently iterating at, right? So basically what we do is, well, we keep track of what key are we looking for. We know what keys exist in the entire record, and then we know our current position, like where are we currently searching for that key. So the syntax or the implementation basically takes a proxy for the key we're looking for, a proxy for all the fields that exist, and then we take the record itself, or a record itself, and then we call our type family saying, well, given this key and given all these keys and values that exist, what is the return type here, right? And then we also get two cases. Case number one is, hooray, our key we're looking for is actually at the beginning of the list of all possibilities of our record, and also the return type that we're looking for is actually this value here, right? And in that case, we can just take our const field, the value here, and return it, and we're done, right? So very easy, first case. The second case is, well, we missed, or the key is not in the front of the list, right? So here we have this key. We know that this key is not equal to the front of the list, and we have like the rest here, and the whole thing here, and this is like what comes next. So basically what we have to do is, well, we continue to read in the more case here, right? And then we iterate again. And then we have like a small helper function that makes sure that we don't have to pass the proxy for all, because when a user calls into this function, we know that the thing that passed in is equivalent to the all here. And this works really well, so we have some example reads here. So we call read record of proxy foo on our example record we had earlier, and then we get like a type bool, a type int, and this is also inferred and works pretty much as you would expect. And if you're trying to read a field that you don't have, for example, BA2R, you will get a type error saying that like there's no instance for this, no class instances. So what can we conclude from this? Well, this works. This is actually not too tricky to implement. Like you can see, it's a couple of lines of code, and you basically have like a basic record system that works. But if you think about it, there's a lot of indirection, right? So every time we want to read a field, for example, well, we have to cycle basically through the whole thing to find like a certain key. Or if we want to like do some more other operations like combining two, we also have to read and like iterate through both, right? So that's not great. So how can we improve this situation? So let's look at some existing implementations. So basically, Vinyl and Bookkeeper are two that are, I think, one of the older ones, or especially Vinyl is one of the older ones, and basically they use this approach a little bit more generalized. So this one, on the type level, gives us more functionality, but it still has this indirection. The same goes for Bookkeeper. It basically is the opposite direction of Vinyl, so it has more specialized implementation of this, but it's also a linked list. So then there's a very smart idea which RAR and labels implement. So basically, I'll show you in a bit, they leverage tuples to represent this. But this has a problem that you need a lot of type class instances. And then I wanted to mention this. There's also something called classy lens, where basically you have template Haskell that generates a type class for every field your lens has. So this can solve some problems, but you still don't have like first-class records at your hand which you can like combine and make unions with, right? So let's look at this tuples case. This tuples case is actually pretty smart because, well, we have tuples, and inside the tuples we basically have tuples too. And tuples, like I think GHC defines them to a size of 32 or something, and you can, I think, set a compiler flag that gives you even more if you want that. And the great thing is also they're pretty well optimized, right? So the optimizer knows how to work with tuples. So this approach is actually really, really fast. There's no indirection here. This works. But what's the problem here? Well, you have to define a lot of type class instances for all forms and shapes and sizes, which is, you can basically take two opinions here. One is like, well, you can just write like a CPP like preprocessor macro, right, that generates this for you. But anytime a user wants to use your library, then they have to do that with their own type classes that they want to implement for this too. So I found this a little bit painful, and that's basically one of the reasons I was motivated to see if we can improve the situation. Cool, so let's talk about SuperRecord now. Basically, one motivation was, well, physical representation matters, right? Because it's a record, it's like a central data structure. We use it a lot, we read it a lot. So we want to make this fast. And not only we want to make it fast, but also we want to make it efficient in terms of how much memory we use up, right? So let's look at, we could just have a hash map or a map underlying, right? Use that, right? Because we have keys that are strings, and we have values. But basically, the annoying thing here is that if you do that, you still don't have linear access, right? So basically what you have is you have like a hash function that has to run every time you pass in a key, or you have the ORD constraint that like builds this tree every time you want to do a lookup. So that's not great. I mean, the normal Haskell list just is out of the question because it's just a linked list, so we don't have to worry about that. So then, well, there's vector, right? Vector is great. It's like a flat array. And one thing we have to figure out is, well, we have keys that are strings, and the vector, has indexes. So how do we map between the two? But we could figure that out. But still, the vector does bound checks. So it's also not like the most straightforward way that you would want this. So then there's SmallArray, which is a very low-level thing in GHC. And it lives in GHC prim. Basically, it's an array that doesn't have a card table. What a card table does is it keeps track of changes if you have a mutable case, so that it knows which parts of the array the GC must retraverse or must not. But the good news is that since we're having immutable records here, what we do is we create this array for a short period of time, this mutable case, fill it with values, freeze it, and then never mutate it again. So that as the mutable array only lives for a very short period of time, we don't run into this problem. And another restriction of this small array is, well, it only allows up to 265 fields, but I think if you have more than that, then maybe you should reconsider your data modeling. At least I haven't, but there has been someone that has tried to work and make this thing smartly at compile time, figure out if it should use small array or array. But we ran into a different problem that I will go into later. Cool, so now we've decided, okay, so we're going to pack all our values into a small array. So how does that look like? Well, we're going to define this record thing here, which also, as we already know, will track on type level, again, these pairs, a type level list of these pairs, which key maps to which value. And underlying that, we'll have the small array, and the small array holds value of type any. Any. Okay, we'll get to that. And then additionally, we'll define, again, this nice tuple syntax here with the addition that you also have a value level version of it, which takes like a proxy type of thing of this with this label, and then we make the value strict here, right? Because we like strict things. We don't want. This is like in this implementation, you don't necessarily need that, but I'm a big fan of making data types strict to avoid space leaks. Great. And then for this field proxy, we will implement the overloaded labels type class, which will give us this nice pound syntax for free. So back to the any. Why do we do any here? Well, we could also not use any here and use typable machinery, but the problem is if we use typable machinery with a safe cast here, then we have two problems. One, this typable constraint will be everywhere, right? So basically, anytime you want to put any value in your record, the value has to be implement typable. Well, that's not too bad. That's also not great because native records don't have that restriction, right? And we want to be as close as possible to what vanilla Haskell data types allow us to do. There's also some argument about performance. I haven't benchmarked this, so I'm not very confident about this, but essentially you still have to do, when you do this cast, there must be some kind of runtime checking that confirms that the types match up. But my argument is, well, if we get the SuperRecord library right once, we never have to worry about this whole thing again, right? Because like my type families will give you the guarantee that the thing you casted to any will be of that type when you read it back. Although you could argue there's no proof, like there's no formal proof, and if I messed up my type family implementation, then you're gonna have a very hard to debug problem here. Cool. So now the other thing that we mentioned earlier is, now that we are using arrays or vectors, well, we need some way of mapping our keys back to the original index, right? So basically what happens is, given an ordering of type level, of this type level array here, we basically say, well, if it's in the first place of the array, or in the last place of our array, it will have, it will be in the index 2. If it's in the second place, it'll be of index 1, and if it's in the first place, it's in position 0, right? So basically, you have this type family that will know, oh, if something is in this position on the type level, then it must be also in this position in the array. And the values that we store at runtime are all any, and we basically use unsafe cors to convert between the two. So what does that look like? So this is a lot of type families here. I think basically the top one I already showed you. This is basically the same function that just given a label, what's the type in the record. And this is actually the type family that, or a type synonym with type families that will compute at what position do we have to read in the array. And this is the machinery for it. So the cool thing about this is that since everything is implemented with type families, this will be statically known at compile time, right? So when you actually compile your program, the compiler will know if you read record, foo, then we will have to read the array at position 2, which will be really, really fast. So the read implementation, I'm not gonna, or maybe we can go through it, but it's pretty simple actually. So the record has a size, right? It has to be a known nat, which means, well, it's a natural number on type level, and I can reflect it back to value level. Then we know, well, the vector position of that label in that label list is also a known nat, so that's where we have to read. We know that our return type, if we have this label, is v. And then all we do is, well, first thing is we downcast from the type level the position where we have to read into a integer at value level, and then we index into the small array at that position, and then last thing to do is unsafe cors, so basically convert that any back into the return type that we accept. So here you can see if my type families here are all correct, especially on the writing side and on like more complicated operations, then this will never blow up. But if they're wrong, then that's a problem. And here's what I'm saying. Here you could theoretically do something more safe with like typable, but that will enforce that constraint on you, and it might be slower because you have like a runtime comparison there. That doesn't happen in this case at all. So basically, under full optimization, what will happen is the compiler will figure out that this is a 5, and then this will all get inlined, and at the end of the day, you just have index small array vector, and then the number 5 here, right? So it's a very, very, very cheap operation here. So basically, a generalized form of tuples here, right? So we have like infinite size tuples. And then here's like another example for how would you create this. This is done with unsafe perform IO, but you can do the same with run st, which we've switched to, but I've kept this for like simplicity. So basically an empty array, you allocate an array of size, like a new small array of size 0, you freeze it and you return it and you're done, right? And for some reason the new small array takes a value here, but this value will never get evaluated. So we just put error no value there. I'm not familiar with the implementation detail why that's the case. And then this is the case adding something to it. Now this is a little bit more tricky, and this is the least proud slide to put because it's a very lot of code. So I'll run through just the steps we'll take. Again, we will compute what position do we have to put we know we'll put this, because we're prepending, we'll put this at the beginning, right? We just need the size of we put this at the end, that's the trick. And we know the size of the record, so basically what we do is we allocate a new small array with a new size, so size plus 1, right? We copy all the existing elements from 0 to the size, the old size, and then we write the new thing at the end of that array, right? So in this particular implementation, the order is flipped between type level and value level, but it doesn't really matter, it's just an implementation detail. And at the end, we do freezing again and return it, right? So that way we preserve the referential transparency, the semantics that we expect. So let's see, we have some more time, yeah. And now, there are very nice things you can do here. So basically what you can do is, using generics, you can reflect this Haskell record, or this structural record, back into a normal Haskell type. So basically, if you have a data type in Haskell that has the same field names and the same types as your structural record thing, you can implement, or the library already implements this toNative thing for you, which you just call toNative, and then you get back a regular Haskell type, right? So that's very cool. So there's actually some interoperation that's going on here, so you can write some interesting things. So you can basically have different portions of your program, like start constructing parts of a vanilla Haskell type for you. In the end, you just combine them all and call toNative, and then you have your real Haskell type. You get free fast JSON. So the reason I'm saying fast here is that basically, due to the nature that we know on the type level already how large the small array is we will need to allocate, right? So on the type level, we already know we're going to parse a JSON with 10 fields, for example, right? So we know our small array has to be of size 10. So what our parser, or JSON parser, does is it pre-allocates a small array of size 10 and then just sticks in the fields as they get parsed. And that's actually really fast, faster than what like AIs and generics do. We'll see in the second benchmark. And toJSON also works, which is very trivial to implement, so that's pretty cool. And like the shapes are very similar. So we've implemented a lot of operations. I'm not going to run through all of them, but just a short list. So we looked at construction. There's get, there's set. There's also modifications. So it's like a little bit like a lens-like DSL that you can use there. You can combine two records, so you can say like left record plus right record, and then you get a new record that has both combined. You can map or fold over values in the record. You can convert to and from native. I showed the to part. The from part is also possible. There's like some interop with MTL, so if you're in a reader monad, then there's some nicer syntax, so you can like directly read from the record that's in the reader environment. What's also cool is you can basically generate lenses for your field accessors, and obviously there's JSON interoperation like that comes out of the box here. Cool, so let's make some short remarks. Let's make some short remarks. So one problem with this approach is that if you construct this naively here, then look at this and this record, right? They're going to have different types because I swapped the order of the fields here. So the top one is name and age and then nil, and the other one is age and name and nil. So these types are different. So if you're only arguing about things structurally, that's totally fine. But if somewhere in your code you have like explicit type annotations like this, then these types won't match up. So that's kind of annoying. So what we did here, it's just an ergonomic improvement, it's not strictly required, we will sort the records, the fields, right? So on constructions, we have a type level merge sort implemented that will sort the things so that they will always be in the right order. This is something that's not strictly required, but this makes construction nice. So these two in the real SuperRecord library would actually have this type here, right? Because age becomes for name. Yeah, another remark to make is, well, type class instances. Well, we're talking about structure, not nominal things. So any instance you write, which you can here, you just have to write one instance, is global on the structure thing. So you're not like, it will be for any SuperRecord that you use, right? So it's unclear if that's what you want or not, what you not want, right? So I think PureScript has the same problem, and they don't allow you to define type class instances for naked records, so you have to wrap them in new types if you want that. But this is more of like a discussion topic. Another remark to make especially in regard to the keynote yesterday evening. There's a lot of copying needed here, and the construction is expensive, right? Because we have to, copy the array every time we add a new field. So we could do like an index construction monad that does this pre-allocation trick that the JSON parsing does internally too. Or if we had linear types and we knew that we were the only person that was holding this thing in our hand, then we could also do in-place operations and preserve the functional semantics of the records, right? Cool. So last but not least, benchmarks performance, record success. It's slightly slower than native or the tuple, but I'm talking about slightly because we're talking about very small nanosecond things. But it's certainly faster than the linked list. The writing part is actually very interesting. So we're 3 times slower than native records here, but we're 10 times faster than the linked list approach here, right? So there's a huge gap in performance. And if you think about JSON parsing, we're 2 times faster than JSON with generics, right? So this pre-allocation trick actually helps a lot. I was wondering when I wrote this if there can be some trick done with generics and JSON too, but I haven't dug into that. Cool, so wrapping up, performance is good. It's economic to use. Theoretically, we can support 265 fields, but remember, I said I want to come back to this. So practically, there's a huge problem, compile times. And this is a real problem because I think right now, depending on how beefy your machine is, after 8 records, you're basically dead. Your program won't compile with optimizations anymore. The reason for that is that some simplifier thing is going on, and I think it's growing exponentially, or at least quadratically, with the size of amount of fields you have. So we've started digging into it, but I've recently seen that there has been a bug fix to this corner case of a simplifier somewhere that's landing in GHC 8.6, so maybe that will improve situation, but for now this is very, basically a roadblock blocker for really adapting this confidentially. You get free lenses if that's your thing, and another cool thing is we've also implemented GHC.js support, so if you're compiling it for GHC.js, we won't use, or we can use the SmallArray, but you can give us a flag, and then instead we will just use native JavaScript objects. This is really cool because that means you get free FFI interop. You can take any JavaScript object that is JSON-y, right? It shouldn't contain constructors and magic like that. But if it's JSON-y, then we can just you can just load it and use it as it was the JSON thing, and there's no conversion needed anymore. So that's pretty cool. Right, cool. That's the end of the talk. Here's the classic compiling joke, and ask away. Thank you.
Just a quick question on your last slide on the compile times.
Yeah.
Did I hear you right? And you said that beyond 8 fields in a record.
Yeah.
Ooh, okay.
Yeah. Yeah. So we're if you don't compile with optimizations, it'll work with more fields. But the whole argument of this is if you compile with optimizations, then it's just an index access. So you want to compile with optimizations. So I think this is a problem in GHC somewhere. First, we thought it was a type level sorting, but even without that, that's not the issue. So there's some inlining simplifier thing going on that just blows up. So we should put more work into getting that fixed, yes.
I don't know if this is encouraging or depressing. I'm the primary author of a Scala generic programming library called Shapeless.
Okay.
It has a record system which is quite similar and similar vintage to vinyl. Mm-hmm. It's used very widely in production. I get complaints from people using records up to 500 or 1,000 fields.
Okay.
And I'm currently working on benchmarks with selecting the last element of a 500 element record.
Yeah.
And it turns out that
but you mean
actually runtime performance is really not the issue. I mean, it uses basically a cons list, linked list representation as the sort of the first iteration you showed. Compile times have always been the biggest thing.
Yeah.
And my reading of the code that you showed is that no matter how much sort of O1 runtime index access you have, all of your operations are going to be linear because you're doing the the standard sort of inductive process working your way through type level lists.
Well, theoretically, that should be optimized away completely.
Well, theoretically, but by the sound of it, it isn't.
Sorry?
Theoretically, but by the sound of it, it's not.
Well, practically it is also. So if you look at the machine code generated, it's like very similar, or like almost the same.
I mean, the compile time process, the type checking process,
yes.
is going to be linear. Because,
yes, correct.
Because you're working through. So
yes.
Runtime is no problem at all. Actually, I've rarely ever had any complaints from people about runtime. It's always been compile times.
Yeah.
And one of the things that at some point I want to investigate is alternative type level representations which aren't working in terms of linear structures.
Yeah.
Some kind of tree-like structure is a possibility. But that's the biggie, actually. Runtime's never been a problem, always compile time. So
I think in this case, what makes it slow is actually not, or I don't think it's the type checking. It's actually like the inlining and optimizing and simplifier that has the problem here. But yeah, like as you said, like we're only at 8 records now, so I don't know what it'll look like with 100 or thousands.
Yeah, so I was recently playing with another library that you didn't mention. I thought maybe you've heard about it, the row types.
Row types?
Yeah, and I've heard many people use it in production, at least due to Reddit, if you believe it. But yeah. So if not, it would be interesting for you to check out and maybe tweet about it. Yeah.
Cool.
Thanks.
Yeah, thanks.
So you mentioned that for your records definition, you have this sorting of the fields so that they are, so that if I understood correctly, you have two definitions that are the same type.
Yeah.
In your example, the actual implementation also was corresponding to the type definition, but does it mean that you could have a type definition that is sorted and that is different than the ordering that you put in implementation?
Yeah. So on the slides, I have the version of code that doesn't care about sorting at all, because just like the codes were already really long. But in the sorting case, you have to do a little bit more tricky things because you have to reorder every time something gets inserted. So the real library takes care of that. Yes.
Okay, so it does mean that your type definition can be different than what looks like implementation. Like for example, if I say string int and when I implement it, I do int string.
Yeah.
Does it work?
Yeah, that works.
Okay.
Yeah.
Cool.
Any other questions?
Very intriguing. So given that you're using this index scheme with SmallArray, and this is really classification to further my understanding of how it actually works, and given that you have these row constraints, am I right in assuming that if I've got a function with a row constraint, like this record includes R, and I access that, then what happens at the calling side, there are dictionaries being constructed which encode because in order to know in which index you have to access, you have to know how big the whole thing is. But at this point, you're parametric over the exact size. So then the dictionary which has to be constructed at the call side needs to include the complete indexing code for the particular case of the record which is being type instantiated at the call side. Is that correct?
Yeah, that's correct. So the has key, record value type class that I showed earlier, or type family, in the real library, it's not a single type family, but it's a type synonym for like a bunch of type families that will get passed in. Yes.
Okay. Thanks. Very nice.
Okay, I think we are running a little bit out of time. Let's thank Alex once more.
Thanks.